Hello everyone. So in the previous lecture we have completed the expression of the classical thermodynamic functions in terms of F. So F is the key factor of this chemical statistics, and likewise every branch has such a parameter. In quantum mechanics, wave function psi, that is the main thing. You have to do everything with psi. Okay, so here in chemical statistics we have to do everything with this partition function F. Also you have learned solid state chemistry. There what was the key factor? The unit cell was the key factor there, isn't it? So everything you had to do with the unit cell. So here also you have to do everything with the partition function. Okay, now you can now find out any thermodynamic property from the microscopic property of a system. And you know the properties of the microscopic systems are available from quantum mechanics. So from quantum mechanics via statistical mechanics to classical thermodynamics, it's a very fantastic and very exciting journey. Okay, so such as you have dealt with the problems particle in a one-dimensional box. Okay, the 0-point energy calculation, the Hamiltonian energy. So those are all microscopic properties. Now from microscopic property to macroscopic manifestation of these microscopic properties with the help of W, that is probability, thermodynamic probability, and then probability to entropy. So there is a very beautiful relationship among them. Okay, so in the previous lecture, as the expressions were deduced, so it is now it is now high time to apply these expressions. Only finding out the expressions is not sufficient. You have to apply this in determining to a system. Okay, so in this regard I am going to discuss a numerical problem from which you will be very excited to know that the energy levels, from the available energy levels, you can find out all the thermodynamic properties. Okay, so that is the beauty of this branch. So the problem is for a substance. Suppose the name of the substance is A. Only two energy levels are available. Okay, where the separation is 881 centimeter inverse and the temperature is 298.15 Kelvin. That means the room temperature. So, and here it's also said that the ground level is closely packed doublet. That means the G0 is 2. And definitely since about the first excited state nothing is said, so G1 is definitely 1. Now you have to calculate the internal energy U, S, A and Cv. Okay, for 1 mole of a substance. Here look at this, 1 mole, that means you are given Avogadro number of substances. These are all classical particles. Okay, they have to be distributed in two energy levels where the ground state has a doublet. Okay, that means G0 is 2 and the first excited state is just above 881 centimeter inverse in the energy profile. So in the that means energy axis, it is just above 881 centimeter inverse. Okay, so you have only two energy levels, and then from this system you can easily calculate the internal energy, entropy, work function, heat capacity, and so other functions also. So how to do this? Let us try to find them out. So this is the picture drawn here. Here the ground state, which has a closely spaced doublet, and here the first excited state where the G value is 1 and the energy separation is 881 centimeter inverse. Okay, and the total number of molecules or the particles is definitely Avogadro number, N0 6.023 into 10 to the power 23, and the energy. So you have to find out the energy of the first excited state because the separation is epsilon. So in terms of arc you have to find them out. So E equals to epsilon equals to h nu or hc by lambda or hc nu bar. You all know about this. H is the Planck's constant, which has the value 6.626 into 10 to the power minus 27 arc second. Okay, I am doing it in the CGS unit. If you want, you can do this in the SI unit also. In that case, you have to put minus 34 joules second. Okay. Here the velocity of light in the CGS unit is 3 into 10 to the power 10 centimeter per second. If you wish to do it in the SI unit, then you have to put 3 into 10 to the power 8 meter per second. This way. Okay. Now nu bar is the wave number 881 centimeter inverse. Okay, this is already given. So what is the value of epsilon? The value of epsilon is just hc nu bar, and the result is we are just putting the respective values. Okay, the value of h, this one, the value of c, this one, and value of nu bar is this one. And the when the units are multiplied, then arc would be obtained. You can also verify that. Suppose Planck's constant, arc second, centimeter per second. So this second inverse and second would cancel each other, and here centimeter inverse, then these two will be cancelled by each other. So arc would be left uncancelled. Okay. So the value is 17.5 into 10 to the power minus 14 arc. So what is the value of partition function f? The partition function must be sum over I 0 to 1, isn't it? Gi e to the power minus epsilon I by kt. Since this is not a non-degenerate, it's a degenerate system, so we have to take into account the GI factor, okay, the statistical weight factor. So if this series is expanded, then we can write G0 e to the power minus epsilon 0 by kt plus G1 into e to the power minus epsilon 1 by kt. Now the value of G0 is 2, while the value of epsilon 0 is 0 because it is a ground state, while the value of G1 is 1 and the value of Boltzmann factor is e to the power minus epsilon by kt. Okay, so the result is, this is nothing but 1, so it becomes 2. 2 into 1 equals to 2. Okay, and here the exponential part is as usual, and here we know that K is the Boltzmann constant, here K, and T is the temperature. So we know the value of K, it is 1.38 e to the power minus 16 arc per Kelvin. T is the temperature, which is 298.15 Kelvin, and the value of epsilon has just been derived. Okay, so let me put this value to find out the value of epsilon by kt. So in order to find out the value of the Boltzmann factor e to the power minus epsilon by kt, we have to find out the value of epsilon by kt first, and in this regard we have put the value of epsilon 78.5 into 10 to the power minus 14, and the value of k 1.38 into 10 to the power minus 16, and the value of T 298.15 Kelvin, and the result is 2.253. So the e to the power minus epsilon by kt value should have e to the power minus 4.253 equals to 0.142. Okay, and the value of f is what? Now the value of f was here in this case 2 plus e to the power minus epsilon by kt. Now we have got the value of e to the power minus epsilon I by kt. What is the value? Now the value is 0.0142. So the overall value is 2.0142. So this is the value of f. Then what should be the value of ln f? The ln f should be the natural log of 2.0142. That means 0.7. So we have got the value of e to the power minus epsilon by kt, the value of f, the value of ln f, and also we have in our hand the value of epsilon by kt also. Okay, now the value of dln f by dt, isn't it? Most of the expressions there are derivative expressions, differential expressions are left, so we have to now differentiate the value of ln f. So we have got the expression of f as 2 plus e to the power minus epsilon by kt. So the value of dln f by dt should be actually 1 by f df by dt, isn't it? Definitely. And the value of df dt is what? No, the value of df dt is the differentiation of 2 plus e to the power minus epsilon by kt with respect to temperature, and divided by f. Okay, so divided by f means 1 by f into the differentiation of this factor, and the differentiation of this term is actually differentiation of two things. One is differentiation of 2 with respect to t, another is differentiation of this Boltzmann factor with respect to t. Okay, 2 is a numerical thing, so it's a constant. Okay, so the differentiation result is 0 here, and here the differentiation should be what? Now differentiation should be, this part should be repeated, e to the power minus kt will come out, and then e to the power minus epsilon by kt will be differentiated. So ddt of minus epsilon by kt. In the next step, first of all the minus term, so this -1 for this minus term, and then epsilon by kt square, because this is t to the power minus 1, so it will become t to the power minus 2, that means kt square in the denominator. And finally the result is 1 by f. This two negative terms are cancelled by each other, so 1 by f to the power minus epsilon by kt into epsilon by kt into 1 by t. Okay, so this is the final result of the differentiation. Now we have got all the values. We have the value of f, we have the value of e to the power minus epsilon by kt, even we have the value of epsilon by kt, and the value of temperature also. So what is the value of 1 by f? Now the value of 1 by f should be 1 by 2.04142. The value of e to the power minus epsilon by kt, now 0.0142. The value of epsilon by kt, 4.253. All the values have been earlier derived. Okay, and the value of 1 by t is 1 by 298.15. So the result is 1.005 into 10 to the power minus 4. So this is the value of dlnf by dt, and we in our thermodynamic expressions we have this expression dlnf by dt in most of the functions. So let's start to find out the classical thermodynamic functions, the values of the classical thermodynamic functions. Let's start from internal energy U. So the expression of internal energy U is what? Now nkt square by into dlnf by dt. So put the value of n, it is Avogadro number. The value of k, it is 1.38 into 10 minus 16 in the CGS unit, and t square means 298.15 whole square, and the value of dlnf by dt just you have derived 1.005 into 10 to the power minus 4, and the unit is definitely arc because we are doing it in the CGS unit, and the result is 7.426 into 10 to the power 8 arc. If you would have found it in the SI unit, the value would have been 74.26 joule, isn't it? Okay, now to find out the value of entropy. So entropy has the expression nk-lnf plus nkt dlnf by dt. So put the values of n here. N is Avogadro number. The value of k is the Boltzmann constant. The value of lnf is 0.7 plus the value of n again here 6.023 into 10 to the power 23. The value of k again here, the Boltzmann constant 1.38 into 10 to the minus 16, and the value of t here which is 298.15 Kelvin, and finally the value of dlnf by dt which has been derived already. So it is 1.005 into 10 to the power minus 4, and the unit should be arc per Kelvin. If you combine the units of all these terms, then you must get the output arc per Kelvin, which is definitely the unit of entropy. Okay, and the result of this calculation is nothing but 0.067 into 10 to the power 7 arc per Kelvin, or in SI unit it should be 6.067 joule per Kelvin. Okay, now find out the value of A. Okay, so in order to find out the value of A, you have to write its expression. What is the expression? Now it is minus nkt lnf. You know all these values, put the value of n. Okay, that means Avogadro number, the value of k, the value of t as usual, and the value of lnf as usual 0.7. So the value is minus 1.734 into 10 to the power 10 arc, or it is minus 1.734 kilojoule, isn't it? Into 10 to the power 3 joule. That means if you eliminate the 10 to the power 3 part, then it will become kilo. So it is either minus 1.734 into 10 to the power 3 joule, or if you do not write the 10 to the power 3 part, it's kilojoule. Okay, finally the value of CV. It is little difficult. Okay, you have to listen to this very carefully. What is being done here? So the expression is nk, then del t at constant volume of t square del lnf by t del t. So just try to think over this, how you would work it out. Just pause the video, okay, and try to imagine how you would be able to solve this out. Okay, if you cannot do, then you will play the video and then follow what is being instructed here. Okay, so start from f, the expression of f for the particular disk case. For particular disk case, the value of f is, the expression of f is 2 plus this Boltzmann factor, that is e to the power minus epsilon by kt. So its natural log must be ln 2 plus ln of 2 plus e to the power minus epsilon by kt, and its dln by dt value is the differentiation of this whole thing with respect to temperature. So definitely, so ln something must go to the denominator first of all, then differentiation of this part. Okay, then differentiation for this part actually is differentiation of 2, that is 0, and differentiation of this means differentiation of actually minus epsilon by kt, and this one must come out. So this one as usual e to the minus epsilon by kt, this bracket just neglect this one is typing error, and then finally epsilon by kt square. How it is done, you know all the processes how to do the differentiation. Okay, now just multiply this t square, take this t square to the left hand side, so it becomes t square dln by dt, and this t square dln by dt is similar to this t square dln by dt. So you are going to have one term, isn't it? Then finally whatever would be obtained from here, you must differentiate this with respect to temperature at constant volume. Okay, so the value is t square dln by dt is just the whole thing the right hand side except the t square part. So here it was epsilon, so it is written here, and here the Boltzmann factor, it is written here, and the denominator is multiplied with this k, so it becomes 2k, and this one becomes k into e to the power minus epsilon by kt. Okay, now this is the numerator part, so here the numerator part has been embraced within the first bracket, and the denominator part also embraced within the bracket, but with a negative power, because it is in the denominator, so it is to the power minus 1. Okay, then it would be easier for you to differentiate this, isn't it? So let's differentiate this d dt or del t, because you just know the volume is constant, so whenever if volume somehow comes here, so make it a constant term, but it would not come. Okay, so if you write d dt, it would not be any problem here, because volume term is not at all coming here. Anyway, so differentiation of two things, this part and this negatively powered part. Okay, so how to do this? You have to do this by differentiation of xy. What is the rule? Now x dy d, if you are doing suppose xy with respect to z, then x dy dz plus y dx dz. So that is the rule. So this one constant, differentiation of this one, plus the second part is constant, this part is constant, differentiation of the first part. Okay, so I repeat here, this part constant, differentiation of this part, look at this part. Okay, and secondly this part constant, differentiation of this part, look at here, this part constant and differentiation of the first part. Okay, now follow the rules properly of differentiation. This for this minus 1, here first of all minus 1 you have written, isn't it? This minus 1 become minus 1 minus 1, that means minus 2, so the power has got a minus 2. Then the differentiation of twice k means k only, isn't it? And then the differentiation of e to the power minus epsilon by kt, no, this part is 0, this part is 0, actually you have to differentiate only this part, isn't it? Yeah, this is a constant, two constant is a numerical value, and k is Boltzmann constant, so these two are constants, so the differentiation will be 0 here. The differentiation of this part is what? Now the differentiation of this part is, first of all k is constant taken out, then e to the power minus epsilon by kt is also taken out, only you have to differentiate minus epsilon by kt. So the result is minus 1 into minus epsilon by kt squared. So these two minus would make it positive, so it becomes epsilon by kt squared simply. Okay, now this differentiation, this part as usual, the negatively powered part, twice k plus k e to the power minus epsilon by kt whole to the power minus 1, then differentiation of this one. Okay, so differentiation of this one is very simple, epsilon is constant, so e to the power minus epsilon by kt is taken out. Okay, and this one, differentiation of epsilon minus epsilon by kt, is simply like the previous one, epsilon by kt square. Okay, so simplify this now. I hope the process of differentiation is clear to all of you. Now simplify this. As a part of simplification, we have got finally minus epsilon square k square t square. Then in the numerator, in the of the first part, you have got e to the power minus epsilon by kt whole square. Okay, and in the denominator part, you have got 2 plus e to the power minus epsilon by kt whole square. Then in the second part, you have got plus epsilon square k square t square. Then in the numerator you have got e to the power minus epsilon by kt, and in the denominator you have got 2 plus e to the power minus epsilon by kt. So from this you can easily take this part as constant. So epsilon square k square t square can also be written as epsilon by kt whole square, and it is done here, and you have taken it a constant as a common from these two terms. Okay, and if this is taken as constant, then this part can be written as 2 plus e to the power minus epsilon by kt is what? Now this is f, so this is f square. So exponential part by f's whole square, because here is also power 2, here is also power 2. So this is exponential term by f whole square. So the exponential term by f whole square. And here also the exponential part by f, because 2 plus e to the power minus epsilon by kt is f. You have already derived this. Okay, so this is written here. Now go to the value of Cv. So this is the value of Cv, this is the expression of Cv, and this differentiation part has got the final expression for this particular system as epsilon by kt whole square, within bracket epsilon by epsilon to e to the power minus epsilon by kt by f whole square minus e to the power minus epsilon by kt divided by f. Okay, finally you have got this expression. Okay, now you have all these values in your hand. You have got the value of n, Avogadro number, you have the value of k, Boltzmann constant, you have the value of epsilon by kt 4.253. remember, you have also the value of epsilon by e to the power minus epsilon by kt, the value is 0.0142. value of f also determined 2.04142, and here the same thing. Okay, and here is a square, whole square, and here minus the same thing without any square. Okay, and the overall calculation is 10.52 into 10 to the power 6 arc per mole. Okay, or in the SI unit 1.052 joule per mole. Okay, so this is the value of Cv. So it is possible to do, isn't it? If you are given the energy states, energy levels, and the total number of particles, then it may be primarily a little bit difficult, but it is possible to find out the thermodynamic functions. Okay, so that's all for today's lecture. A few more lectures are left in this chapter, maybe a couple or 3, I don't know. So later it would be found that how many more lectures are required for this chapter, but we are at the penultimate stage, not at the ultimate stage. We are at the penultimate stage of this chapter. So the climax is over now. Okay, now the finishing part, so the batting of the tail enders now left. Okay, so goodbye. Thank you for showing patience in listening to this hectic things, isn't it? Okay, have a nice day.